Okay, welcome everyone back. Today we are very happy to have Andrea Brini, who is going to tell us about quantum geometry and physics of Looijenga pairs. And thank you very much for joining us, Andrea, and please take it away.
Yep, thank you very much for the invitation. I'm just going to start by making a couple of announcements, if that's okay. Because we've got a couple of things happening in Sheffield pretty soon. So this is probably relevant for the typical audience of this seminar. So we're going to have a conference taking place at the end of June, beginning of July. Topic is BPS states, mirror symmetry, and exact WKB. And yeah, the speakers list includes many of the usual suspects, and you're all welcome to join in whatever form it will take. So at the moment, it's still unclear due to the COVID situation whether it will be an in-person or an online conference. But we've got a website, and we'll post updates up there. And the second is we're going to have an opening for an associate or full professor in our department. And I've been mandated to tell this seminar that string math applicants are especially welcome to apply. So so we're a group that's been progressively losing its soul towards mathematical physics, even though we're called algebraic geometry. And by all means, if you're interested, please drop me a line. So it must be going live this week or the next. Okay, back to business. First of all, let me try and explain the title of the talk. So the main character will be some pairs XD, which I call Neff-Looijenga pairs, and these are pairs XD with X a smooth complex projective rational surface, and D an anticanonical divisor in X, which is a union D1 through DL, where DI labels its ith irreducible component, which is a simple normal closing divisor, and each irreducible component is required to be smooth and Neff. So if this language is a bit alien to you, you can think in differential geometric terms. X is a compact real four-dimensional smooth manifold, and which is on top of it is a Kähler manifold, and it supports an Einstein metric with positive cosmological constant. And D is a Riemann surface, a singular Riemann surface inside X, which so the meaning of the word anticanonical is that on the complement of this Riemann surface, X minus D, there exists a holomorphic top 2-0 form, which is nowhere vanishing. So X minus D is a Calabi Yau, non-compact Calabi Yau surface. And one of the consequences of what I've written is that one way to visualize D is as a necklace of holomorphic two spheres in this four manifold that are joined together by some mildly singular point. And that's going to be my character, a surface and the Riemann, well, a four manifold, a complex surface, and the Riemann surface inside it. And I got two classes of results to tell you about. The first is that there are 5 different but equivalent, non-trivially equivalent, stringy and numerative invariants that we can associate to these pairs, X and D. And the second message is that all these invariants are closed form solvable. So either we can solve them all and prove that they are related, or we can compute one, and knowing that they are related, we can compute them all. And this is based on 3 joint works with Pierre Bousseau and Michel Van Gerel. So let me start. Yeah, so the flow chart of the talk will be, these are the 5 classes of invariants that I'll be talking about. So I will consider, first of all, I'm going to introduce each item in this diagram in G course. I'm going to be considering the log and the local Gromov Witten theory of the pair XT, which will be introduced first. And I'm going to show how these will be related by some version of a log local principle postulated in the algebraic geometry literature 3 years ago. And when considering the uplift of this connection to higher genus, it would be natural to relate the log Gromov Witten theory of the pair XT to the open Gromov Witten theory of some Calabi Yau threefold with some special Lagrangian in it. And this connection to open Gromov Witten theory mediates all sorts of connections. Open Gromov Witten theory of Calabi Yau threefolds, special Lagrangians and Calabi Yau threefolds, will mediate all sorts of connections with various classes of BPS theories. And this will be described towards the end of the talk. So let me start by giving a sort of very broad motivation and context for the existence of this talk. So let me start from afar. There's a venerable area of study in geometry, which is given by the study of enumerative questions. So the name of the game is you want to enumerate geometric configurations in some given ambient space that satisfy a given set of constraints. And these type of questions go back millennia. Like first example there is Apollonius' problem, trying to find the number of configurations of osculating circles that meet a given collection of, say, lines, points, or circles in a plane. But the type of questions that you can formulate can get more and more refined and actually get more and more modern as you do it. One classical example question from the mid-19th century is how many lines are there on a smooth cubic surface on an algebraically closed field, which is going to be C throughout my talk. Or, for example, you could ask how many genus 0 degree D plane curves pass through 3D minus 1 points in the plane in general position. Or getting even more modern and closer to the heart of a string math seminar, you could ask how many degree D curves of any genus are there on a smooth projected Calabi Yau threefold, for example, the quintic threefold. Now, the relevance of this question, these type of questions, is both intrinsic. So you're maybe generally interested in providing an answer to some sort of enumerative geometric count, but it also branches out to other domains of mathematics. For example, the sort of enumerative invariants that you can extract can give you some sophisticated information about the ambient manifold itself, especially in the case of symplectic manifolds, or to some spaces that you can construct out of it, for example, connected to knot theory. And the generating functions of these invariants have turned out to have some marvelous properties, relating them, for example, to modular forms. And moreover, they have an independent life and the motivation in itself from mathematical physics, and in particular from topological string theory. So what is an enumerative problem and how would you attack it? So one thing that I would like to stress is that in all these three examples, I'm counting one-dimensional objects in some given target. So I will be specifically consider the case of counts of curves. Yeah, is there a message in the chat? Yeah. So how would you go about in setting up an enumerative count of curves in a variety? Well, you start with X, some given algebraic variety, which would be smooth projective in this talk. For example, you take the complex projective plane. And what you can try and do is you want to associate to X some auxiliary space, which parameterizes the object that you want to count inside X. So for example, the space of plane conics in P2. And step number 3 is you would like to extract the result of your enumerative count in terms of some integral over this moduli space in the form of some quantum invariance. So for example, in the case of plane conics, this moduli space can be a moduli space of quadratic equations in two variables, or homogeneous quadratic equations in 3 variables of degree 2. So you got 6 terms for those, and you don't want all the coefficients to be 0. So you want to eliminate those coefficients, and you want to consider all the coefficients defining your quadratic equations up to scaling. So in that case, you have C6 minus the origin modulo C star. That would be a P5. And what goes inside this integral is some sort of collection of delta function that is supported on the configurations that you want to count. For example, you want to impose that your conics pass through 5 points, no 3 collinear. And one way to realize this incidence condition is through caps of suitable cohomology classes on this moduli space. So for example, for the case of plane conics, passing through 1 point imposes 1 linear condition on your coefficient. So you have 5 free parameters, and you have 5 linear conditions. And the solution to that is an inhomogeneous linear problem, which give you just 1 solution. And in this case, the classes that you would put in here would be the first gen class of O of 1 on P5, the hyperplane class, representing those linear conditions. So that's the sort of like fairy tale expectation. Start from some, you want to count some configuration of curves in a given target algebraic manifold. And well, we want to set up some compact moduli space, which is moreover smooth. And your count should be given in terms of some intersection theoretic problem on this moduli space. And I say that this is like the fairy tale expectation that because that's almost never the case. In particular, it's almost never the case that this moduli space is compact, thereby making this integration and its realization in intersection theory problematic. So one way to tackle this is to allow the presence of some degenerate objects at infinity. So somehow resolve the problem of the ill-definedness of this integral by geometrically, by compactifying x in a suitable way. And various choices are possible. And they give rise to various flavors of invariants that are related to each other. So the sort of moduli space that I will be mainly focusing on throughout this talk is a moduli space that's obtained by viewing curves in a given algebraic variety X as parametrized curves. So I look at them as maps to X modulo automorphisms of the domain. And this is a so-called moduli space of stable maps to X and Gn bar XD, which is a moduli space of pointed curves of arithmetic genus G, and with n mark points in it, P1 through Pn, that are mapped through X with the image of the fundamental class of C being a given 2 homology class D inside X. And I take this up to, as I said, automorphisms of the domain. And one thing that I haven't explained is what is the meaning of this big bar that I've put on it. And that's my choice of compactification. And so if I took C smooth, I will end up with some non-compact moduli space. So I can think of a sequence of maps to my target X that eventually leads to a domain that's singular. And what I'm going to allow is a sort of minimal amount of singularity in the boundary. So I'm going to allow at most nodal singularities in C. And in order to have a reasonably well-behaved algebraic orbifold as the result of this quotient, I'm going to impose a stability condition. And the stability condition is that my map phi is only allowed to to contract irreducible components that have finite automorphism group. So either sufficiently high genus or sufficiently number of mark points. So what is the result of this? Well, this compactification, first of all, does what it says on the tin. It gives me some compact moduli space of expected dimension given by the dimension of the target -3 times 1 minus the genus of the source curve, plus the anticanonical degree of the map, the image of the map, plus the number of mark points. And although this moduli space suffers from all sorts of pathologies, so it's singular, it's reducible, and the reducible components have possibly different dimensions, so it's of impure dimension. It does support at least a surrogate of a fundamental class in the expected dimension. And that's essentially my two ingredients. I have a compact moduli space and some class I can integrate my geometric constraints against, my incidence conditions against. And the result of that is a so-called Gromov Witten invariant. So this will be numbers n, x, g, d. So x for the target, g for the genus, d for the degree, which associate to a given collection of closed subvarieties in X, B1 through Bn. What in scare quotes would be the number of degree D genus G curves through this given collection of cycles. And one way to realize it is to use the fact that we have these mark points, P1 through Pn, and these give natural evaluation maps of your stable mat phi at that particular mark point. So those are maps F1 through Fn from the moduli space to the target, and we can use that to pull back condition on the moduli space. So we can pull back the Poincare jewels of these classes Bi, and if the total rank, we can cap them together, and if the total rank matches the dimension of the expected dimension of the moduli space, we get a number by integrating against the virtual fundamental class. And in sufficiently good conditions, like genus 0 and X a homogeneous space, we can the result of this integral is what would be expected in the smooth case. So it's just the intersection of inverse images of these cycles on the moduli space, the way we would have like the linear incidence conditions in the case of counts of plane conics. So that's what Gromov Witten theory does for you, that we have this auxiliary object and we have this sort of huge data set that we can associate to a given variety given by these numbers, and that represent this type of counts. So let me just show what this looks like in the example of the second question that I put in my first slide. So what is the number of curves in the plane of degree D that are genus 0 and pass through 3D minus points in general position? So this would be, in this case, we have x equals P2. And because the curves are rational, we're counting genus 0. And we have some degree D. And what we want to do is pull back 3D minus 1 point conditions from the target to the moduli space. And this will return my Gromov Witten invariant, this putative count of curves, which in this case turns out to be enumerative. And in the spirit of the times, I just put just a big collection of numbers that give the result of this count. So for degree 1, we're counting lines through 2 non-coincident points, and we know that there's a unique line passing through 2 points that don't coincide in the plane. For degree 2, that's the case that we were considering before. We're counting conics passing through 5 points in generic position. And again, that's essentially a linear problem for the coefficients of the quadratic equation that defines the conic. The result is 1. And then there's some nonlinearity kicking in starting from degree 3. Because in that case, the fact that the curve is rational is a polynomial condition on the coefficients of the equation in 2 variables that defines the curve. And there are various ways, either using the Zoom theorem or by counting singular fibers in some elliptic fibration that tell you that this number is equal to 12. And there's a bunch of other numbers that can be computed for higher degree. I just put 3 of them. And I want to say something qualitative first about these numbers. Well, the first thing is that if I just gave you this sequence, this wouldn't probably ring any particular bell. So if I told you that the first 5 numbers are these 5, it would be hard to guess that the 6th one is whatever this is, 26,312,976. So there's some mysterious pattern taking place in the sequence, at least not entirely obvious. And what is actually springs immediate to AI is the fact that the growth of these numbers is very fast. And one can actually prove that this goes like 3D minus 1 factorial, the number of these points, times an exponential factor. So this was computed, well, it was studied numerically by DiFrancesco and Itzigson 25 years ago. And it's been studied a lot more recently, 2-3 years ago, by Zinger and Qianwei as well. In particular, the Gromov Witten potential, which is the generating function of this, the natural generating function of these invariants, is the Borel transform of the Taylor series having the ND as Taylor coefficients. So that's convergent with radius of convergence 1 over x0, which is, if you will, the singularity, the conical-like singularity of the topological A model on P2. And so these are, okay, not immediately obvious as a sequence, grow very fast, but there is some kind of rule. And the rule is given by some highly non-trivial nonlinear recursion amongst these coefficients, which at the level of generating functions translates into a nonlinear ODE satisfied by the potential. And it turns out that this is up to some change of variables. This is some version of the Penlevet-6 equation. And the recursion is something that reflects the boundary geometry of the moduli space, what we've added to the compactification. It's a consequence of the WDVV equations. And that's what WDVV looks like for the case of P2. So there's a lot going on in the simplest example of taking the plane and taking genus 0. There are already quite involved structures involving some completely integrable Hamiltonian ODE that governs this sequence of numbers. And I want to contrast this with what's going to happen next in the talk. And one of the reasons why the structures are here is that they don't come from, they're just plucked out from thin air. They have an independent life and actually an original life in physics. So at a microscopic level, what Gromov Witten does for you is to give you a mathematical realization of the topological A twist of an n equals 2 to sigma model having X, the killer manifold X, as a target, plus a coupling with topological gravity, and without superpotential. And the fact that there's a topological A twist is basically starting from n equals 2 to sigma model. We redefine the generator of Lorentz transformation on the worksheet by subtracting the U1 vector R charge, which as a result gives rise to a spin 0 supercharge, so a BRST-like charge, whose cohomology is isomorphic to the cohomology, to the rank cohomology of the target. And the space of Q invariant solution under this BRST charge, or equivalent to the solution of the Euler-Lagrange equations of motion in the scalar sector, is just given by the Cauchy-Riemann equation. So in this context, one is considering, by just looking at classical vacua, at some moduli space of holomorphic maps to the target. And the automorphism of the domain is what is essentially a realization of the gauge symmetry. And if one considers only vevs of BRST closed insertion in the topological sigma model, because the energy momentum tensor is Q exact, that reduces to an integral over own shell trajectories alone. So the path integral localizes with probability 1 on the moduli space of classical solution. And this caps of cohomology classes integrated against the moduli space of stable maps to X are the realization of this last point. And at a space-time level, there's another realization of these kinds of curves, which is particularly poignant in a case in which X is a smooth projective Calabi Yau threefold. Because in that case, the topological string is known to compute a particular class of F-terms in type 2A or M-theory compactifications with A supercharges in 4 and 5 dimensions, respectively. So in that language, the set of generator of primitive Kähler classes is in bijection with vector multiplets of the effective theory in 4D.
But here you were studying a massive theory. This was a P2, not a Calabi Yau threefold. So
correct. Yes, you are correct, and that doesn't apply in this case. Yeah, absolutely. So what I'm saying in this slide has this big assumption up here in the top right. X is a Calabi Yau 3. But I'm going to come to Calabi Yau 3s pretty soon. So yeah, whatever I'm going to say in here doesn't have a correspondence in the non-conformal case, like the massive case of P2 that you mentioned. Yeah. So in this case of Calabi Yau threefolds, the genus 0 Gromov Witten generating function will compute the prepotential for this vector multiplex yi, and so the corrections up to second derivatives in the gauge field strength involving all the scalars and the vector multiplex scalars, and the higher genus Gromov Witten generating functions will furthermore compute couplings of this vector multiplex scalars to the n equals 2 Val super multiplet. So there's a very well established and rich story going on here. We have some sort of three pillars. We have a very classical enumerative problem. We want to count configurations of curves in an algebraic variety. This problem has a lot of structure in many cases, which will be parallel here as well. For example, the calculation with WDVV for P2 would be mirrored in this case, will be present in this case as well. And there's the physics realization of this Gromov Witten counts, which would clear interpretation both at a worldsheet and space-time level. So that's a rich story, and a well-known one. And what I'm going to do in this talk is I'd like to step up my game a little bit. And instead of considering invariants of the geometry of X alone, I would like to consider invariants that are sensitive to something that I'll resist the temptation to call a defect inside of X. So I'm going to take X and D, a pair given by a smooth complex projective variety of dimension M, and D is a divisor, a some Cartier divisor, which throughout my talk will be almost invariably anticanonical, and that will be a union of L irreducible components, D1 through DL, and there will be a simple normal cluster singularities at the intersection of these components. And what I'm going to ask is that each irreducible component is both smooth and Neff. So Neff means that DI will intersect non-negatively any effective curve in X. For example, if I set M equals 1, I have X a one-dimensional target, and D is a divisor in it. So it's some collection of points. And I'm going to take X to be P1, the complex projective line. And D, since D is anticanonical, that's just given by 2 points on the holomorphic sphere. So up to PSL to Z, I can take them to be 0 and infinity.
Can you explain a little bit what's the use of setting things up this way. I mean, for example, in this P1 example that you started with, right? We could say, oh, no, we actually have a Calabi Yau, which is just an infinitely long cylinder, which is P1 with 2 points deleted.
Absolutely.
And I know historically there was one sort of reason why here actually, well, the direction I sort of remember is, supposing you understood things like mirror symmetry for something boring like an infinitely long cylinder, right, which is easy to understand, can I then understand things like P1, which you get by compactification? So it was actually going the other way. I would have started with a Calabi Yau obtained by removing the divisor D from X, which is sort of an easy to understand geometry, and then study the effects of compactification as a means of understanding what one would want to mean by, for example, mirror symmetry for massive geometries, which are positive.
Okay, yeah. So what I want to do is, I don't want to go back to X. One way you can think about this is that this is some sort of holomorphic version of just considering some special Lagrangian inside this space. I'm treating, for example, the punctures here. You could just try and think to open them up to give you some boundary circles around these two punctures. And I want to compute invariants that are sensitive to these boundary circles, to the data of these boundary circles. For example, feeling winding numbers around these boundaries. I don't want to go back to P. I want to remember all about the geometry of D. And actually, in the next slide, I'm going to present two separate classes of invariants in 2 slides from now. One that gives you, again, it goes back to the plain vanilla ordinary topological A model on some target that fills both X and D, but there are no constraints attached. I mean, you're not considering that thing with a defect. And the second thing that I'm going to present is something that will fill this divisor by imposing a suitable set of tangency conditions. So there's sort of a finer set of invariants that I want to construct. It's not that I want to use the complement of D as a building block to go back to the complement of D inside X to compute the full story for X. It's probably something more. And it's actually, there's a lot more in terms of invariants I want to compute in that second. But I hope it's going to be clear in a couple of slides. So let's forget about string theory or moduli spaces, maps, or enumerative invariants. I'm just looking at pairs for the time being with a surface and a curve. With a variety and a divisor in it. So in one dimension, that's probably the trivial example of considering X minus D, which is C star, with X equals P1. And in dimension 2, I can take the complex projective plane, P2. And for D, if I start from the case L equals 1, so if L is equal to 1, that means that D is irreducible and it's smooth and Neff. And in that case, D is a smooth cubic. And in particular, it's an elliptic curve inside P2. And if I take 2 components, I have the case of a conic and a line that's not tangent to it. And for L equals 3, D is the toric boundary, is the union of the toric divisors in P2. Some piece of jargon that's by no means completely standard, but that I'm going to use throughout my talk, is that a smooth Neff pair is toric if X is a toric variety, and the complement of D is the toric boundary, is the big torus orbit C star to the M. And I'm going to call it a Looijenga pair if X is a surface, so M is equal to 2, and D is singular. And remember that I'm only imposing single, I'm not considering like cusp singularities or anything like that. I'm just having a bunch of smooth divisor intersecting with simple normal crossing behavior. So in particular for L equals 1, we saw that these should be smooth. So if D is singular, we must have at least 2 irreducible components. And we're going to call an F Looijenga pair tame if the boundary either has more than 2 irreducible components, or each irreducible component has positive self-intersection.
And so your divisors that you're removing are always toric divisors. So in saying
no. That's point. No. That would be the case of point 1, which would give the toric boundary indeed.
Okay, so remind me of the terminology. A conic is what? Is a cubic in P2?
It's a section of O2, and the toric divisor will be a section of O1 in P2.
O2. Okay. So it's a quadratic.
Yep. And so this can be classified, the left Looijenga pairs. And there are 19 smooth deformation types. And 16 of these are tame. So being tame is a sort of generic condition. And there are only 3 wild examples. Well, 16 are tame, or they carry the same Gromov Witten theory of a tame example. So for the purposes of this talk, I'm just going to consider them as tame. Okay, so answering Mina's question now. There are 2 classes of invariants that I want to attach to X and D, and they are very different in flavor. So the first thing that I want to do is restrict it now to the case of Looijenga pairs, Neff Looijenga pairs. So X is a surface. I want to use D to define an embedding of X into some Calabi Yau vector bundle, into some higher dimensional non-compact Calabi Yau variety. And the embedding is by viewing X as a 0 section of that vector bundle. And the vector bundle is defined as follows. I'm going to consider the total space of the dual line bundles to each of these irreducible components, D1 to DL. So that's a rank L vector bundle, split vector bundle on X. And the statement of the anticanonical condition on D is that the first Chern class of this total space is 0. So the fiber contribution compensates that of the base. So that's a Calabi Yau 2 plus L fold, 2 for the base and L for the fiber. Yeah, so if we go back, so the case number 1, in this case, we would have O minus 1 plus O minus 1 on P1, the result conifold. The case 2I would be the case of the total space of the canonical on P2, O minus 3 on P2. And the case 2 and 3 would be higher dimensional Calabi Yaus. So we have O minus 1 plus O minus 2 on P4, and 3 copies of O minus 1 on P2. Sorry, O minus 1 plus O minus 2 on P2, and 3 copies of O minus 1 on P2, which is a Calabi Yau 5-fold. And what we would like to compute now is the first class of invariants I will consider are the invariants of this total space. So naively, we would like to compute in genus 0, starting in genus 0, the number of degree D rational curves in the total space that pass through a given collection of points in general position on the 0 section X. And so the message of the beginning of the talk is the sort of drill that you have to run is, well, you need to have some modular space that parameterize these curves in this total space. And then, well, hopefully get something compact out of it in some way and define some suitable intersection theoretic problem starting from it. That's the sort of 3-step procedure. And so the first question is, do we get a compact moduli space of stable maps to this total space, which is non-compact. So some non-compactness can be thought to be in order. And now if the stable map intersect generically each irreducible components of capital D, then a stable map to this total space is really a stable map to the 0 section. And the reason is that the H0 of the pullbacks of these line bundles has to vanish because of Neffness. So in particular, there is no way to deform holomorphically a stable map of the 0 section if this intersection is generic. That's one of the reasons why we get a compact moduli space of maps to the result conifold, a super rigid P1. So as a schema, moduli space of stable maps to the total space is the moduli space to the base. However, the natural obstruction theories differ in the two cases. And that's encoded into some obstruction bundle, which at a smooth moduli point given by a curve C and a stable map phi is just the H1 of the pullbacks of this line bundles, direct sum.
Sounds like some kind of engineer problem. Why are we studying this particular thing? I'm sure you'll tell us in the end, but somehow it feels like you're telling the story backwards. Maybe you should give us a preview. Why should we study this particular thing?
Okay. Can I just ask you to wait for a couple of slides? It's going to be there very quickly.
Okay, so element points, are they determined by the divisors?
Okay, yeah. So let me put it simply. This is sort of, well, in the case L is equal to 1, which is the case in which the divisor is smooth and irreducible. This is a well-known story. It's just the total space. It's what people call a local surface. Total space of the canonical on some final surface. So local P1 cross P1, local P2. This is a familiar object, and I'm considering just a tiny tweak in this well-known story, where I'm considering higher dimensional spaces as well. And the difference that this will entail at the level of invariance is that I will need to consider some non-trivial insertions to make up for the fact that I'm going to have some extra dimension in the moduli space. But yeah, that's essentially a higher dimensional version of the usual local Calabi Yau story, which is going to be relevant for a different set of invariants momentarily. So the virtual fundamental class on the space of stable maps to this Calabi Yau total space will be defined as the virtual fundamental class of the base intersected with the Euler class of this obstruction bundle. And if you compute the rank of this guy and subtract that to the expected dimension of the formula for the expected dimension a couple of slides ago, you see that the expected dimension is equal to L, the number of divisors, irreducible components in the divisor D, plus the number of mark points minus 1. So in particular, if, again, to make contact with the well-known case of Calabi Yau 3s, if you have only one component, L equals 1, so we have Calabi Yau 3, say local P2, and you have no mark points, the expected dimension is 0. That's the familiar effect that the Gromov Witten invariants are just the degree of this virtual fundamental class. And in higher dimension, what I'm going to do compared to that, to the simple Calabi Yau 3 case, is that I'm going to pull back L-1 point condition on the 0 section. And this will saturate this expected dimension, and they will give me a number. There's a collection of numbers that I can compute for higher dimensional Calabi Yau manifolds. These are actually the only Gromov Witten invariants that you can compute in this setting. So yeah, so at the moment, the answer to Mina's question is slightly unsatisfactory. There's something that makes contact with the usual Calabi Yau 3 story, and I can do it, so why not? That's it for the time being, but it will improve in a second. And the reason why it will improve is that there's a second set of invariants that will turn out to be related to these. And these invariants have a completely different flavor. So nothing happens on a Calabi Yau. I'm not considering a space that I construct out of X and D. I just consider the Gromov Witten theory of X, but I use D to impose some tangency condition, some sort of kissing condition at the irreducible components Di. And what I would like to compute now is the number of degree D genus-zero curves in X that pass through L-1 points in general position in X, and that have maximal contact order at each irreducible component. So the intersection of a stable map of degree D with Di will generically have the intersection number D intersect Di intersection points. And I'm looking here at the maximally degenerate situation in which all these points collapse to be a single point of maximal contact order.
What does maximal tangency mean?
Yeah, so one way to think of that is that if you think D is defined by some equation, say y equals 0 in some coordinate y, then and you have some coordinate z on some affine coordinate z on your source curve C, then the map locally there around the origin will be something of the form y equals alpha z to the intersection number d point di. So instead of having a curve that intersect each di at the expected number of intersection points, I'm imposing the condition that this coalesce to be just one. I'm going to show a picture maybe in a couple of slides, so that will be possibly more clear. Okay, so one would like to run the drill here as well. So one would like to compute to first of all define a moduli space of object like this, hope to get something compact, and define some virtual fundamental class and extract Gromov Witten invariants out of it. But the story here is significantly more complicated than the usual case. And there is immediately a problem with compactness that comes from the fact that we have this maximal tangency conditions on this boundary divisors. And so you can think of having like a sequence of open stable maps to X with given contact orders and DI. And that in the limit of this succession, the sequence will have maybe some irreducible components developing that fall entirely into the divisor. So that the tangency condition doesn't even make sense in the limit. And there have been different approaches to tackle this. One could take the Zariski closure in the modular space of stable maps. With that create problems at the virtual level that I'm not going into. There's a well-developed theory of in the case in which D is smooth due to Jun Lee. This would be the relative Gromov Witten theory of X relative to D. But that becomes, again, significantly more complicated in the case in which D is singular, which is what we're treating here. And the sort of technical device that can be used in this case, and it proves to be very effective, is to view X as a log scheme for the divisorial log structure given by D. So in that case, one can come to terms with the fact that there's a non-compact moduli space, and that in the limit, what happens in the compactification may have some irreducible components that fall into the divisor. But the information about the maximal tangency, what the contact orders is remembered in terms of homomorphism of ghost sheaves. What the upshot of that is that there is a moduli space of log stable maps that record this type of numerative objects, and that's compact. It's proper log-Deligne-Mumford stack of curiously the same expected dimension as the one of the previous slide. And if X is log smooth, it supports a virtual fundamental class in the expected dimension. And log Gromov Witten invariants, recording this count of degree D genus curves with kissing condition on the divisors, can be computed exactly as in the previous slide by pulling back point conditions on X and integrating against the virtual fundamental class. So let me present some examples. That's the main justification for presenting the case of the Gromov Witten theory of P2 without divisors before. And I'm going to consider what will be my running example, which is P2 with a line on the conic. So in this case, well, in the picture here, where you're looking at a degree 6 rational curve in P2, you would expect that to hit the line in 6 points, but I'm insisting that it's tangent with the maximal order 6 in P2. So it looks locally you got something that looks like y equals x to the 6. And that passes through 1 point. We have L minus 1 points. So for L equals 2, that's 1. And it's also maximally tangent to the conic. And since the conic has degree 2, then the contact order is 12 in this case. Now, as for the case of P2, the Gromov Witten invariants turn out to be enumerative. So they're honest integers that do what they say on the tin, that they return the desired enumerative count. And I'm just going to compare this with the sort of mysterious sequence that we had for P2. So first of all, the invariants grow a lot more slowly than they did for the case of P2. And you can see that you can show that the growth is only exponential in this case. So the generating function of this log Gromov Witten invariance has radius of convergence 1/4. And as a matter of fact, you can give a closed formula for these numbers. It was hard to guess what would be next in this sequence, but for these ones, these are essentially Catalan numbers. Well, up to a linear factor. So they're essential binomial coefficients 2D choose D.
Are you going to explain to us what does log Gromov Witten invariance mean? Physically, I suppose, because the ordinary ones, of course, they're familiar from topological string. I mean, they are the topological string invariants. What are the log Gromov Witten invariants physically?
Physically, that opens. It's what I'm going to propose in this talk is that geometrically they can be essentially realized as open Gromov Witten invariants on a threefold, and something that is extremely well known. And in the case in which the surface is toric, and at least a subset of the divisors are toric, this will be toric branes in a toric Calabi Yau 3. Okay. And there will.
I thought you mentioned that you had like 5 enumerative invariants, and they were all related by string dualities or something.
No, they're all string.
I actually really loved it if there were a physical interpretation of these guys and a physical interpretation of your local guys.
They're all string motivated, and that's true. And
great. What are the motivations?
Okay, sorry. Yeah. It's fair point that for the log invariants, there is no immediate interpretation in string theory as you would have for the ordinary ones or for the open ones with boundaries on some.
I'm perfectly happy with open GW. I know what that is. I think you yourself mentioned that these log GWs, you wanted to say it's like some kind of defect partition function or something.
I said I want to resist the temptation, and I probably should have. One way to look at these as having some sister open theory, which naturally lives in 3 dimension and it has as boundary condition some special Lagrangian.
Sorry, so just maybe you could just tell me from that. I thought what you were trying to tell me during this talk was some string duality and a mathematical explanation of that string duality.
No.
You're saying here are 2 math things.
No. They're okay. There are all the 5 corners in the diagram that I presented have a mathematical independent life, and they're all string motivated on their own. The first connection that I said I would present, which is some sort of equality between this log and local invariance. So while the local invariants have a well-defined mathematical, in the case of at least smooth divisors, have a well-defined physical incarnation in terms of the ordinary topological A model on a Calabi Yau. I can't reproduce the same. I can't give you a physics incarnation for the log ones. But there will be a well-defined mathematical connection between the two. How to interpret that in terms of some string duality, that's not something that actually I understand in a minute. What will be motivated by string duality is the connection of the local theory with the open one in terms of some geometric engineering on higher dimensional Calabi Yau targets.
I see. So again, real quick, could you just tell me the motivation of connecting this log theory to anything else for you?
Okay. I was gonna say it in. So I'm gonna go back to. So you're probably asking about this first top row over here. So the motivation for this. So first off, I at the moment I don't view the equality. Well, I'm actually going to describe in a second how what this looks like.
It's fine. I can imagine like inequality, like that's okay.
Okay. Yeah, exactly. Okay, that's okay. If we just imagine it as an equality, I can what I claim to be able to do is I have a well-defined set of invariants coming from some sort of generalization of relative Gromov Witten theory to the case of singular divisors. So something that's well-defined as a purely algebro-geometric object to something that is not only well-defined algebro-geometrically, but has also physics incarnation.
I see.
And I can do that in two ways. So there's a connection in genus 0 that essentially equates the log invariants to the local ones, even though they have a priori and geometrically nothing to do whatsoever with each other. You're doing very different things. In one case, you're looking at maps in a compact surface with some ramifications and some tangency conditions at the divisors. And in the other, you have an unconstrained count of stable maps in a higher dimensional Calabi Yau. It's not even the same space, but these turn out to be one and the same class of invariants. Mm-hmm. And moreover, there's I'm sorry because I'm giving away my punchlines, but yeah, it's probably good to do it now.
Yeah.
One way of looking at this at an uplift of this correspondence that I'm going to show in genus 0 for higher genera, when the local Gromov Witten theory doesn't make sense anymore. Well, there are essentially no higher genus Gromov Witten invariants for higher dimensional Calabi Yaus, is to reread the local Gromov Witten theory of the higher dimensional Calabi Yau space in terms of the open Gromov Witten theory of a Calabi Yau 3 with some special Lagrangians.
Understood. Okay, gotcha.
And that's something that you can see from the engineering in genus 0. And the proposal is that since these two gadgets compute the same effective terms in genus 0, the natural set of invariants that you obtain by coupling to gravity, by looking at, say, the effective 2-2 theory that you obtain by compactifying on a Calabi Yau 4, are the natural counterparts of the higher genus log invariants up here.
Gotcha. Okay, excellent. Yeah. So just to summarize, you're saying this log thing was something natural called relative GW in the case that you had a smooth divisor or smooth anticanonical divisor, but there exists an algebro-geometric generalization thereof. So like, what the hell is it? And you're saying, well, on the one part, we can go to this higher dimensional local situation, but that's only good for genus 0 at most. But there's this other open picture where I can also define it further and conjecture that I have some refined open/log correspondence. And okay, cool.
Yep. Okay.
Thank you very much.
Okay, doc. So I was showing you a bunch of numbers. And yeah, so even though I'm considering a much more intricate geometric situation up here. So I'm either considering this higher dimensional Calabi Yaus, or I have this more complicated counts of maps in P2. The numerology that's behind it seems to be slightly simpler than the case of just plain vanilla Gromov Witten theory of P2. This is a fact that I'm going to explain will be a completely general feature of this net Looijenga pairs. And moreover, there's a relation, at least at a numerical level, that you can witness between the log and the local invariants. And that's given by some, again, this is something that we can guess what it is. I think we've got some sign factor, and then you have some square law, which is 2D squared. And if you try and do the same thing with the case of P2, log theory of P2 relative to the 3-coordinate axis, again, the numerology simplifies a lot more. So in this case, I won't offend you by asking what's going to be next in this first column. You can see that this grows, again, a lot more slowly. It only grows polynomially. And it's indeed just a square law. And once again, the ratio of the log invariants versus the local ones has some pattern, which is some sign factor times d to the cube. And what's been observed by people, so by Takahashi in, I guess it was around 2000, and then much more recently by Graeber Hassett, was that this relation between log and local invariants being proportional by some sign factor times something like d to the L is completely generic. Well, it's fairly more general than just these two simple cases. And around 3 years ago, people smelled the coffee, and they proposed that the log invariants are related to the local invariants by they're essentially equal up to a universal factor. The universal factor is some sign factor given by the intersection numbers of D with each divisor plus 1 times the intersection itself. And so, okay, there's some statement which we saw to be satisfied in the previous two examples. What is the evidence behind this? Well, the evidence is that this is a theorem in the case in which D is a smooth divisor. So we have just D is irreducible, smooth and F.
Sorry, I lost you a little bit. Why do we call the local ones local? The local ones are invariants of a compact X.
No, the local ones are the invariants of the total. So it's
is the total space.
Some people would call the result conical local P1. It's not a very physicsy terminology.
So in that sense.
In that sense.
So it's of the total. Again, so remind us, which question are you asking in the Calabi Yau? So if you're building Calabi Yau on X, and
I just want to compute the topological A model in genus 0 with target that Calabi Yau. And the Calabi Yau is constructed as that vector bundle, sum of O minus DI over X.
But you're still asking, I'm just looking at the transparency back then. You say the local invariants are counts of degree D genus 0 curves through L minus 1 points.
Correct.
So I see. Okay. Okay, so the L derivatives or L minus first derivatives of the pre-potential.
Correct. Yeah. In one way of looking at that. Okay. Let's stick to the familiar setting, which is L equals 1, and we get a Calabi Yau 3. So and the way we're looking at a Calabi Yau 3 that looks like your surface and the normal one. You just have a Calabi Yau 3 that contains that surface, and you zoom in a neighbor of that surface. Then the normal bundle will be just a canonical bundle for the Calabi Yau condition. For example, O minus 3 and P2. In that case, what this is telling you is that up to a sign, the generating function of the log invariance. I assume that's what you meant when you said first derivative. Is that because I'm bringing down this D times DI terms? So if I compute the generating function of these guys, so that the way you would compute the generating function, you write down a generating function would be you would sum over degrees and have something like e to the d times t. And what this is telling you in the case of a single component is that you have the generating function of Gromov Witten invariance for a Calabi Yau 3. So for D smooth, sorry, for the case that corresponds to Calabi Yau 3 on the local sides, which is D smooth, is the logarithmic derivative with respect to the Kähler parameter, the exponentiated Kähler parameter. So it's q d dq, or if you want d over d dt, where t is the natural flat A model Kähler parameter, of the generating function of the ordinary Calabi Yau, the ordinary topological string partition function in genus 0 for that local Calabi Yau.
I was just reading off from your definition, right? If you in topological string, right? If you want to have invariants that pass through G points or D points, you take D derivatives, right? Because I see. And these D derivatives would have exactly, I guess, given you the right-hand side.
No, because it's two different spaces.
Sorry, right? The L minus 1 derivatives.
It's two different spaces, right? So if you wanted to compute like the Gromov Witten invariance with, say, L minus 1 divisor insertions, well, first of all, you have L in here, so even that doesn't match. But if you had like if you wanted to compute L minus 1 divisor insertions in here, that would be exactly that derivative that you were talking about. But then the moduli spaces that you're looking at are different, so that you have no guarantee that the numbers are the same.
I was only talking about the right-hand side.
Yeah, correct. Yeah. Okay. In that case, we're in full agreement. Yeah. Absolutely. Yeah, absolutely. You can phrase it in that way.
So,
okay.
Can I ask a quick question?
Yep.
It's been a while since Busso's talk, but my vague recollection was that the logic, the way I like to think that it made sense to think about this correspondence went through the open Gromov Witten invariants, where at least physically, where you think of the okay, so the open Gromov Witten invariants that you're counting, I should think of as being at infinity in the Coulomb branch, right? That's the point in moduli space at which you're
Okay.
counting.
Yeah.
this thing.
Yeah.
And so then my vague recollection was there that you relate the open GW counts to the local counts by replacing the divisor at infinity with something about the local geometry. This is my very vague recollection. Does something like that make sense, or is it right that I can physically think about some sort of degeneration that relates the open GW geometry with the local geometry?
It's difficult to think about degenerations because things are occurring in different dimensions on the two sides. So in one case, you're just looking at the surface, and in one case, you're going L dimensions up. And in the case of Busseau's talk, that would have been 1 dimension up. I don't think that's probably the best way to think about it.
Maybe it was the log counts were naturally related to the open counts, and again, there it was important that you were counting the open things at infinity. I remember it was important for relating something to the open guys, that just the geometric picture, that you were counting the open invariants were at infinity. How do I see that here?
When you said infinity, you said at infinity and the Coulomb branch. Do you mean like near a large volume? Is that?
Yeah.
Was that at infinity in the moduli space? Well, in that case, if you have a relation that can be phrased as some sort of equality happening as some sort of perturbative equality, well, some sort of perturbative relation, which is essentially a matching of some type of coefficients in some natural worldsheet expansion, that would definitely take the form of just Taylor coefficients on the left-hand side equal to some triangular transformation involving the ones on the right-hand side. What this is saying is that this is diagonal and this is the coefficients in a sense. So as a matter of fact, I will not talk about this here, but there are cases in which you can consider singular phases as well. So when I will stick throughout this talk to the case in which X is smooth, but there are generalizations to orbitals that I will mention briefly towards the end. So I'm not sure. I'm not sure in that sense how that's how relevant it is that we're sitting around large radius. This is just some relation. I'm just saying that the generating function for the log guys is well, as Mita said, is some logarithmic derivative of order L, given by L divisor insertion of the one on the local side. Now for this, there is an equality that can be proven at the level of virtual cycles. In a case in which D is smooth, and there's a further proof of the correspondence when the DIs are hyperplane sections. So under some strong positivity condition on the DIs, which are not just required to be an F. And so with Busseau and Van Garel, we proved that the correspondence holds as well when X is toric and D is the toric boundary. And what I'm going to tell you about in this talk is that this holds true. So the statement for toric pairs was in all dimension. If you stick to surfaces, we can prove a stronger result that tells you that the full descendant log and local Gromov Witten theory in genus 0 for an off Looijenga pair is closed form solvable. And as a corollary, you can try to see if the local correspondence holds, and the answer is yes. So what's the idea behind the solution? The idea, this is essentially largely Berkeley developed technology over the last couple of decades.
Sorry, Andrea, we were, just a second. So this was supposed to be very informal. We were having some chats in the chat, and I think it's actually better to do it. Okay, maybe Michael can just tell his comment, just so we can like all be on the same page. Because then what you're saying, with his comment, what you're saying sounds actually very familiar, I think. Michael?
Let me see.
Or you can just read what he says, and maybe you can comment.
Okay,
maybe that's a better way.
Yeah. So yeah, general comment. So the expectation is that the Lagrange Witten theory of X and D is the candidate algebraic theory of the open Gromov Witten theory of X minus D. And yeah, I think Michel thinks of looking at some Lagrangian on a nearby SYZ fiber to D, with the tangency exchange with the winding. Oh yeah, with Lagrangian near D. The problem with the open theory is that we don't know how to make sense of it in algebraic geometry. Is that a fair summary of your comment, Michel?
Yes, absolutely.
And that specifically requires the Lagrangian you're considering to be at infinity in the Coulomb branch.
I mean, you could have Lagrangians inside, but you kind of think of this as some sort of limit where we're moving them all to infinity.
But would you expect a correspondence with some log theory if the Lagrangian weren't at infinity?
No, because you cannot make a tangency like a divisor appear in the interior.
Yeah, awesome. Okay, good. This is, I think, what I was remembering from Pierre's talk.
Yeah, he was talking about this sort of limit which maybe is what we're thinking about with moving the Lagrangian to infinity. Maybe.
Yes. Yeah, good.
Then if I'll just say briefly, then what this reminds me of actually, it is open closed string story that basically instead of studying a model with Lagrangians, you can, sorry. There's a correspondence between a model and a Calabi Yau, and a Calabi Yau in one. Oh, no, it's been too long. I think actually probably Max might remember this better. In going up a dimension by basically turning on adding branes to turning fluxes, because this kind of correspond. It sounds like what one is just trading is like discounts versus
that's going to
zero with higher number of hole counts. That's the kind of generalization you're talking about. And we are just going up. The more holes you add, the higher dimensions we go up.
That's going to appear in a second. Yeah, indeed. Okay. Yeah. So
okay. So it sounds. Let me just tell a story, and you can tell me I'm wrong because it's probably wrong. But this is my vague recollection now of how I'm putting these things together. So the local side is you're geometrically engineering some 5D field theory probably. You can think of that alternatively as compactified on a circle, I guess. You can think of that alternatively as some D3 brane probe of some surface. And from that picture, you get some open Gromov Witten count. And I can now, via the picture we just discussed, give that open Gromov Witten count an actual math definition via log Gromov Witten theory. So in this sense, I'm relating the local through to the log via open Gromov Witten. Is that a sensible story?
That's one sensible story. And basically this what this talk is doing is considering a higher dimension version of that compactification in empiric story. So you're going to compactify to so you're going to have effective theories that live in lower dimension. You're not going to have like a theory on R4 times S1. For example, in the case of P2 with the line and the conic, you will have something that lives on R2 times S1. some n equals 2 theory, or in the case of type 2a compactification, something that lives in an n equals 2 theory in 2 dimension, which alternatively, you can, instead of realizing it as an effective theory, you can engineer it by wrapping d4s on some special Lagrangian on a Calabi Yau 3 this time around. That's sort of trading things that you're doing.
Okay, good.
So the Calabi Yaus are becoming higher dimensional compared to that story. So the engineered field theories will be lower dimensional because that's what you're compactifying. You're partially compactifying on.
And okay, well, in what sense does it make sense to do BPS state counting in such low dimensions? Like, you can't have charged states below 4 dimensions, right? So,
well, you can have, well, in the context of in the context of the theory, the open theory on the threefold with the Lagrangian, which has not appeared yet in the talk. These are just, it's just Ooguri Vafa type BPS type counts.
okay, good. So these are,
so
you're shooting a super potential.
So you have, so you have M2s ending on M5s in in 3 dimensions with the M5 wrapping some special Lagrangian in the Calabi Yau 3.
Okay, good. So yeah, you can just think of those as instantons instead of BPS states. You're still in 4 dimensions, I would say.
No, in that case, no, you have 2 extended dimension.
Sorry. Yeah, good. Okay.
I mean, it's a theory on the D4 that you're looking at.
Okay. So yeah, based on this physics picture, you don't expect to be able to go up to arbitrarily large Calabi Yaus, right?
No, but I can geometrically.
You can.
That's
okay.
I can. Okay, geometrically, there is an identity of invariance that goes up to dimensions that don't make sense in string theory. I have an example of a Calabi Yau 6-fold for which the log local correspondence holds, including its open theory uplift in terms of counting holomorphic pairs of pans in a toric Calabi Yau 3. And yeah, that's, I was expected to say that in 4 or 5 slides. But yeah, that will be the case. Okay, so I said there's some bestiary of examples that points in the direction of an identity of these invariants. And my claim in these 2 slides is that I can prove that identity. And I can prove it by proving something more, which is I can compute each member of say the left-hand side and the right-hand side of that equality in closed form. The reason why there was this closed formula for 2D choose D for the invariance of the line and the conic in the plane is the most simple example, is the simplest setting in which I can perform that calculation. But that holds for any Neff-Looijenga pair. So let me tell you how this goes. So the idea is that the theory of this higher dimensional Calabi Yau can be reconstructed from the theory of the base by a series of classical theorems of Geventhal's first and then Coates-Geventhal's. And sorry, I got stuck. Yeah. So the idea is that one can reconstruct the J function, so the generating function of genus 0, 1-point descendant invariants with arbitrary powers of psi classes of the total space from that of X. And so the question is, okay, so if we can compute the theory of the total space from that of X, what is the theory of X? So that hence the relevance, for example, of looking at the topological model on P2 to reconstruct the theory of local P2, O-3 and P2. And so how do we compute this J function of the 0 section? Well, the 0 section by this Neffness condition on the divisors is always some weak final surface. It's, well, except one case, it's always some Del Pezzo surface. And the quantum cohomology of Del Pezzo's was solved a long time ago, about 25 years ago by Klemm Pandharipande. One could use that to compute the J function, but there's because there's a bound in the Picard number of imposed by the Neffness of X. We can compute that by degenerating to a toric model in all cases, and use toric mirror symmetry. And the only price to pay in deforming to a toric model is that that will extend the Neff cone of curves by an additional set of -2 curves that become effective in the degeneration. And this will compute not trivially to the mirror map. Now, the statement of tameness is that the mirror map is trivial in those cases. In the non-tame case, there's a non-trivial mirror map that can be proved to be algebraic, and either by explicit Lagrangian inversion or other methods, one can show that it has an inverse, which is given by essentially some rational function of many variables. So that means that the mirror map is either trivial or it's closed form invertible. And since the B model is closed form computable, that means that the A model has a closed form expression for the 1-point invariance. And the multi-point invariance can be reconstructed using a reconstruction theorem of the small j function, which is what's computed by toric mirror symmetry, to the full big J function. And that's essentially a statement of using WDVD. And if you're not familiar with these methods, long story short, there's an explicit formula that computes the Gromov Witten theory of this total spaces constructed from a smooth Neff Looijenga pair for all x and d. And for the log side, there are two tools. One is an explicit comparison statement that relates the log and the local invariance with the predicted prefactor using essentially the degeneration formula in Gromov Witten theory. And there are two settings that one can consider, either the case of two components or the case in which the pair is tame. In particular, remember that a pair is tame if it has more than two components or all self-intersections are positive. So in particular, if you consider these two cases separately, that covers the full set. And now the way the story goes in the tame setting is that Gromov Witten counts of a toric pair. Most of our pairs are not toric, like the line and the conic, can be reduced to by classical theorem. It's generalization of classical theorems going back to Mikhalkin and Nishino-Siebert to account of graphs in the fan of X with some incidence condition. And what's non-trivial though is that for any Neff Looijenga pair, not necessarily toric, there's a Sarkis of link type construction that relates its invariance to the ones of a toric pair. This can be encoded combinatorially in terms of some scattering diagram, some algebra of broken lines of Gross, Hecking, and Kiel, and Gross, Pandharipande, and Siebert. And the statement of tameness is that essentially the combinatorics behind relating the tropical counts to the log counts is particularly simple. That means the statement of finite scattering. And again, if this was slightly technical, but the punchline is there's an explicit formula, and it matches the one of the previous slide with the predicted prefactor. So that will be the end of some talk. So we know that in genus 0, this Vangerel-Graeber-Ruddat conjecture holds true for Neff Looijenga pairs. However, that's the beginning of the headache for this talk. And this comes when one wants to consider some refined information that's encoded into the higher genus theory.
Sorry, the story about scattering.
Yeah.
Can we generalize away from X being 4-dimensional? I mean, 4 real dimensional? Or this is about the 4 real dimensional X?
So for this talk, X will be a surface. And there's the generalization of what I'm going to say to higher dimension is at best unclear. There is a general story in a paper of Gross and Argutz from last July, which considered an extension to that setting. But how that fits in that story is not clear.
What are they counting in higher dimensions? What replaces the scattering? What do the scattering diagrams look like in higher dimension for higher dimensional X?
I'm not really sure. Michel, do you know how to comment on this one?
Yes. So maybe scattering diagrams work in all dimensions, and what you will see as being raised correspond to like just codimension 1 walls, and they're all decorated with some wall crossing functions, and there's really complicated algorithm, and the wall crossing functions are generating functions of log Gromov Witten invariants. Very much like this idea that the open Gromov Witten invariance should be, computing the mirror, etc. What is very special in dimension 2 is that we can really compute the full scattering diagram. So in higher dimension, there's an algorithm, but not necessarily a full computation.
So in higher dimension, the scattering diagram is codimension 1 in the real toric base. Did I get that right?
Well, so you have, okay.
I just need it roughly, just so I can place the story somewhere.
Yeah. So roughly, maybe you can think of, you have real codimension 2. So you have some sort of real affine manifold of dimension n, and then you have real codimension 2 walls, and they could be infinitely many of those. And the whole idea of the scattering diagram is that you add order by order corrections. So you might start off with I don't know, very few of these walls, which have some wall crossing functions attached to it. And then as the walls meet each other, they produce new walls that come with new wall crossing functions. And the thing which is so special about dimension 2 is this process of adding new walls is very, very well understood. But it is a very, very, very complicated story. And just to summarize, these log Gromov Witten invariants are the generating functions that give you the wall crossing. Anyways, I hope that's helpful to some extent.
Okay, so trying to consider, so all this story happened in genus 0 up to this point. And so one question would be, to what extent does that generalize to a statement for all genera? And what kind of invariance would be involved in that case? So what one could try and do is, well, consider the genus G setting. So the moduli spaces log stable maps to XD in genus G without mark points. And the expected dimension of this moduli space goes up, as it would in the case of the ordinary Gromov Witten theory, by G. It doesn't stay constant as it would do for Calabi Yaus. So that would spawn extra zero modes that you would need to soak up in some way. And the traditional way you would do it is you would add in higher genus extra insertions that would compensate for that. And but there's a sort of canonical way of sticking to the same number of insertions. So that should be, sorry, an L-1 of points in the surface, and compensate for this extra, this excess G dimension by the insertion of a lambda class on this moduli space. So that's the top churn class of the Hodge bundle on the moduli space of log stable maps. So the fiber of this guy would be the vector space of holomorphic differential on your curve, and that would be a rank G vector bundle. And one can cook up some generating function with some formal parameter h bar, which I'm going to call log q. H bar equals log q of so some generating function that will depend on this formal parameter. And one of the main results of Bousseau's thesis is that the tropical calculation that gave the genus 0 invariance carries through unscathed to the calculation of this set of higher genus invariants, up to promoting the tropical multiplicity in the Mikulkin-like count to its Q analog. So one can bootstrap entirely the scattering calculation for genus 0 to a calculation of closed forms for the full higher genus invariants with this type of insertion. And essentially for free. So we have one side of the equality that gets generalized to all genera basically just by Q deformation of the combinatorics that's behind it. And then one natural question is what happens to the right-hand side, which was the local side. So how can we compute what's the substitute in higher genus for the right-hand side? One would guess maybe it's higher genus local invariants. And it turns out the question actually doesn't even make sense when L, the number of irreducible components, is greater than 1. So we have a Calabi Yau n-fold with n greater than 3. And the reason is that the expected dimension becomes negative when the genus is greater than 1. So there's not even a moduli space to play with. So there's essentially nothing that can even play the surrogate of a higher genus local theory to compare with a log invariance, with this class of log invariants. So what's the way around? And the way around is that this Gromov Witten invariants of local Calabi Yau n-folds are n-3-fold open Gromov Witten invariants of local Calabi Yau 3-folds, which makes sense that higher genus, and we propose that these guys are the natural counterpart for the higher genus log invariants with insertions of lambda classes. And so I should probably spend a few words telling you about this, these open invariants. Now, if you start from C3, there's a gazillion different ways of presenting it as a total space of some completely integrable, Hamiltonian completely integrable system. And one is the Harvey-Lawson fibration. So in that case, if you have Z1, Z2, Z3 affine coordinates on C3, you have moment maps that are given by differences of square moduli, the square modulus of Z1, Z2, and Z1, Z3, and the imaginary part of the product of Z1, Z2, Z3. And so the generic fiber of this moment map is a compact 2 torus times R. So you have a 2 torus containing the fibers that's given by rescaling Z1 to e to the I theta 1, Z2 to the e to the I theta 2, and Z3 to e to the minus 1, e to the minus I theta 1, e to the minus I theta 2. And then you have a real line that's given by the real part of this product. And that's what happens generically. However, there are special fibers which are obtained when 2 of these affine coordinates are equal to each other and to 0, in which you're basically strangling the neck of one of the 2 circles that make up this T2. So you have an S1 times the union of 2 paraboloids joined at their tip. And picking either of them would give you essentially R2 in polar coordinates times S1. And these special fibers is what I will be concerned with. This was studied extensively by Mina and Kumran 21 years ago. Now, if you consider not C3, but a general toric Calabi Yau 3-fold that's projective over its affinization, which basically means it's a symplectic quotient, the picture that you get for the discriminant locus, instead of being just one trivalent graph, will be a bunch of trivalent graphs, so trivalent vertices glued together. And if you isotope that picture a little of the discriminant locus, what you will obtain is some planar lattice graph with the Lagrangians sitting somewhere on a point in that graph. And if you're familiar with toric geometry from the fan perspective, the way this planar lattice graph is obtained from the fan is essentially as the dual graph of it, by exchanging edges with tangent edges, faces with vertices, and vice versa. And the datum of a singular Harvey-Lawson Lagrangian will be given by a decoration of one of the edges of the fan. So sorry, the fan will be a cone over the dual graph of this planar lattice graph representing the discriminant locus. Now, there are several approaches to defining open invariants of the toric branes, either by relating to the relative Gromov Witten theory of some formal neighborhood of the toric skeleton of the variety, or by using localization in generic degrees specified by some general relative homology class y to L relative to L. So here I split this as an absolute homology class and some winding number contribution nu. And the upshot of that is that there is a moduli space of open stable maps to Y with boundary in L and with absolute degrees and winding specified by beta in some partition nu, which has expected dimension 0 for all genera. And the open Gromov Witten invariance will be given by the degree of the associated virtual fundamental class. And I can arrange them together, as I did for the higher genus log invariants, as the Taylor coefficients of some generating function in Q. So Q is e to the G string, essentially, the genus counting parameter. Now, if I start from a tame Looijenga pair, so except for 3 examples, I can always construct a semi-projective toric Lagrangian pair. So a toric Lagrangian in a toric Calabi Yau threefold as follows. I can take, first of all, I can consider the complement of L-1 irreducible components. The order will not count for the calculation of Gromov Witten invariants inside X. So for example, the case of X equals P2 and the line of the conic, I can take away the line from P2, and I will take the total space of O minus the remaining divisor over that complement. And by the anticanonical condition, this is the canonical bundle on this quasi-projective complex surface. And so it's a total space of the canonical on some surface that's a non-compact Calabi Yau threefold, which moreover, if X is toric and the divisors that I've deleted are toric, will be a toric Calabi Yau 3. And starting from these divisors that I delete, D1 through DL-1, I can define L-1 special Lagrangians that are incident to the non-compass torus orbit, torus 1 orbit that intersect DI. And there's a canonical identification of the degrees with the relative homologies degrees in the Calabi Yau threefold. And let me show this in a cartoon, just in the running example of P2 with a line on the conic. So if you start from this this tame pair, I start from P2, and this is the fan of P2. And what I do first is I delete a line, which means deleting any of the 3 toric divisors of P2. So the complement of, say, the line z equals 0 in homogeneous coordinates for P2 is just affine space A2. That's the fan of A2. And what the procedure instructs me to do is to take the total space of O minus 2 over C2. And that's a trivial bundle, so it's just C3. So what I obtain is, now this picture is a cone over this diagram. So it's a single smooth cone in 3 dimensions, and that's the fan of C3. And the datum of the Lagrangians, so in terms of the dual graph, so reversing the procedure before of recovering the discriminant locus starting from the fan, will be given by a single vertex. And the locus where the Lagrangian will sit, corresponding to the deletion of the line, will be the one that precedes the position of D in the cyclic order for the vertex. So it will be sitting here. And there's an issue that I'm not delving upon too much, which is what choice of framing does this naturally come equipped with? And yeah, maybe I'll just say a word. There's the natural framing of the Lagrangian that we associate to a pair XD is the one such that the framing vector recovers the moment polytope of the base surface when it's completing all the way up to the next edge. So in this case, we would have like a framing vector that goes all the way up here, and the region enclosed would be the moment polytope of P2. So it would be conformally equivalent to that moment polytope. And the conjecture is that this guy in genus 0 will give the same local invariance of the local space O-1, O-2 on P2, and the same extends for any smooth net Looijenga pair, regardless of the number of components, provided that it's greater than 1. And in higher genus, the higher genus log invariance will be computed by the higher genus open invariance with a prefactor that is a combination of 3 things. So there's a Q analog, a promotion to its Q analog of all the intersection multiplicities that appeared in the VGGR comparison formula. There's an extra factor that takes into account the multi-covering contribution for higher genus open invariance. And there's a condition that fixes this factor uniquely by imposing that when Q tends to 1, we recover the classical factor. So it's some formula that one can think it's true. And spoiler alert, it will be true. Now, the motivation for this has already been discussed. And it's a higher dimensional version of geometric engineering. So if we started, so there's a very well-known story that relates the Gromov Witten potential of certain local Calabi Yau 3s to the pre-potential in the omega background, well, in the self-dual omega background, in the case just of the higher genus Gromov Witten theory, of some gauge theory obtained by type 2A compactification on the Calabi Yau, or M theory compactification on the Calabi Yau, giving an effective theory in 5 dimensions with 1 compactified. And there's a somewhat lesser known story that if we try and do the same thing 1 dimension up, then the Gromov Witten potential, the ordinary Gromov Witten potential with pointer insertions, with codimension 2 insertions on this local Calabi Yau 4-fold will compute well, the superpotential for the low energy effective theory on R2, or in M theory on R2 times S1. Now, there's another way we can engineer superpotential terms in terms of holomorphic curve counts, and that's through holomorphic discounts on a local Calabi Yau 3-fold. And again, this is something that we've already discussed, and we have 2 potential ways of interpreting superpotentials in theories in 2 and 3 dimensions in terms of some topological amplitude. And it just so happens that sometimes the same superpotential can be engineered in both ways. So for toric Calabi Yau 4-folds, we can realize a superpotential in terms of a holomorphic discount on a toric Calabi Yau 3 with certain toric branes. So this was put forward by Meyer around 1999-2000 by noticing that the Picard-Fuchs equation in relative homology that govern the holomorphic discount on a toric Calabi Yau 3-fold with toric branes are the GKZ system of some toric Calabi Yau 4-fold. So when this happens, the same quantity can be computed in 2 different ways, and therefore these 2 quantities are the same: the holomorphic discount in 3 dimension and the ordinary Gromov Witten count in dimension 4. Now the proposal, as I said before, is that this is true in higher dimension. So in particular, if we compute annuli in ending on toric branes in a toric Calabi Yau 3-fold, that computes the ordinary Gromov Witten invariance of a local Calabi Yau 5-fold. And the same holds true in the 1 case that we have for a count of holomorphic pairs of pens in a toric Calabi Yau 3-fold, and the ordinary invariance of a Calabi Yau 6-fold. Moreover, this holds true for more general toric brane setups than the one considered by Meyer, and we're forced to consider non-canonical choice of framings for the correspondences to hold between local and open invariants. And
by non-canonical choice of framing?
There, you can consider the vertex in canonical framing, and the framings that will occur in this construction will always be non-canonical, will always be shifted by, for example, 1 unit from canonical framing.
Okay, I thought there was no such thing as a really totally. Okay, never mind. Okay, I see. But this is nice. So what you're saying is that basically these are all techniques of essentially always computing open Gromov Witten invariants of a Calabi Yau threefold. Just not with one stack, not with one brain, but potentially with many brains, except that if you want to kind of turn this into a closed string, you can't turn it into a closed string Calabi Yau fourfold. It turns into higher dimensional Calabi Yau geometries, but it's always the same original question of open open Gromov Witten invariants of the original Calabi Yau 3. That's why X is being a surface is special, I suppose, because it's special, because only then you have Calabi Yau threefold with brains.
Yeah, absolutely. So yeah.
Okay, so that makes sense.
Yeah. And remember that there was this a bit of a conundrum how to give a refinement of the right-hand side of the log local correspondence, because there are no higher genus local invariants. And what we postulate is that the natural replacement for that in higher genus, which in genus 0 returns exactly local invariance, is given by the higher genus open invariants, for which we always have a virtual fundamental cycle in expected dimension 0 in all genera, since we're living on a Calabi Yau 3. So that's the slogan, higher genera. On the open side, refine the log local correspondence. So that's where this comes from. That's where this complicated.
Sorry, say it again. What's the higher genus counterpart of the closed string?
Well, we postulate that. So you have the open string, and the open string count makes sense at all genera. But for the closed string count, there is no counterpart of higher genus closed string topological A model on a higher genus Calabi Yau. And the reason is that the virtual dimension of the moduli space of stable maps to that Calabi Yau becomes negative. So you have basically one codimension to insertion in genus 0, which is what's allowed. You always, as for any Calabi Yau, you have the unpointed Gromov Witten invariance in genus 1. And starting from genus 2, the expected dimension is 0. So there are essentially no Gromov Witten invariants that you compute that you can define. So somehow there's an asymmetry between the log and the local story when you go to higher genera. And the proposal is that the surrogate for the higher genus local story is given by open counts on a Calabi Yau 3, which do make sense in higher genus. Does it make sense?
Keep going.
Okay. Okay, before I tell you why or whether this is true, let me tell you where this can go. So we have this relative counts on a surface, which is almost a classical problem in algebraic geometry. So like in the running example of P2 with a line and a conic, we just have some simple configuration of the plane, and we want to enumerate stuff that passes through a bunch of points and has some kissing condition at the divisors. And if we believe that we can construct out of that a toric Calabi Yau threefold with a toric Lagrangian and relate in a definite way the higher genus log invariants to those open invariants, well, that's a setting where essentially all our wishes come true. So we know mirror symmetry is special, and open mirror symmetry, open string mirror symmetry too, in the case of Calabi Yau threefold. And we know the mirror symmetry is special in the case of toric varieties. And here we're looking at a Calabi Yau 3, which is a toric variety. And in particular, to attain Looijenga pair by essentially 12 years of recent history in the study of the topological string of the toric Calabi Yau, we can interpret this log invariance in terms of, well, home-fly invariance of Salarge and dual Chern-Simons theory. We can compute them to all genera using a variety of calculational schemes. These are localization of moduli spaces of open stable maps or the topological vertex. And again, this log invariants have a statistical mechanical model that can be attached to them, either in terms of random matrices of crystal melting with defects corresponding to the brain, or some webs of some free Fermi model. There's a classical 1+1 integrable hierarchy, which is a reduction of the two-dimensional Toda hierarchy that computes these invariants. So we have a set of bihamiltonian integrable equations that compute these invariants. There's a higher genus. This is a bit of a propaganda slide, I have to admit. There's a higher genus reconstruction theorem in terms of periods or residues on the Ooguri Vafa mirror of our toric Calabi Yau in terms of remodel B model. And moreover, something that you wouldn't suspect just from Gromov Witten theory alone is that there's some finer integral structure underlying these invariants because they are morally open invariants of a toric threefold in terms of open BPS counts. And related to that, we can reformulate these open BPS counts in terms of the DT invariance of some symmetric quiver. And of course, all this as an effective theory interpretation, either in terms of surface defects in a four-dimensional gauge theory or some vortex partition function. So for example, in the case of, if we take X to be the blow up of P2 at one point, and we take D1 to be the inverse image of the line, and D2 a smooth member of the linear system generated by the other toric divisors, the associated toric pair is just a result conifold with some framing. So the corresponding log invariant can be computed either from the Kohler Holmfly of the unknot, the resolvent of some matrix model, there's a tau function of some integrable system. It can be computed from the remodel B model, and it corresponds to some quiver, symmetric quiver, which is a quiver with two vertices and one self loop. So if we blew down this exceptional curve, we will return to the case of P2 with a line of the conic, and we will have like the Volterra hierarchy computing those invariants and just the frame vertex, which I presented before for the calculation of the open invariants. Okay, so we have all these connections. How can we make good use of them? For example, for starters, to prove the conjecture. And as a second step, to compute something that we didn't know how to begin with. Now, for most of these have some applications to Gromov Witten invariants, for example, the calculation in terms of residues from the Ionel or Anten recursion, but they don't tell you anything generally new about these invariants that you didn't know how to compute before. So what I'm going to say today is a combination of point 2, 6, and 7. So I'm going to use the topological vertex to prove the conjecture, and then 6 and 7 will prove something genuinely new about these local invariants and the log invariants and the local invariants as well. So let me start. And well, the first theorem is that the higher genus Gromov Witten theory of a tame pair. This is the higher genus version of the first theorem I presented. Both of these theories are closed form solvable. In particular, the open Gromov Witten theory of this toric brains associated to these Looijenga pairs have closed form expressions in the winding number basis coming from the topological vertex. And as a corollary, one can check that the higher genus log opens correspondence holds as proposed. And well, the proof is a direct calculation systematically of all the higher genus log invariants of X and D and all the higher genus open invariants of Y and L in closed form, both as function of Q and which is e to the G string, and the degree variables, so beta and nu for the open theory. So from the log side, this follows from the Q deformed scattering diagram. So the Q deformation of the ordinary scattering diagram calculation for the genus 0 theory. And from the open side, this can be computed in closed form from the topological vertex. And this seems like something that's very well established, but there are some genuinely new formulas that one has to produce, for example, for some skew-short functions on the topological vertex side in order to reproduce the formulas that one has on the log side, and vice versa. So there are predictions from the topological vertex that are genuinely new expressions for Q hypergeometric series that we had to prove or were proved a couple of weeks ago in a paper by Christian Krachtenthaler. So this method of proof is very divisive, depending on whether you identify primarily as a mathematician or as a physicist. So as a mathematician, you have the price to pay for the ignorance in relating these two theories in terms of some geometrically meaningful relation connecting different moduli spaces is turned into the need to prove a much stronger statement, which is a full solution for both ends of the equality, and that you can witness the equality as a result. As a physicist, there's one of the cases where you have that moment of elation where you have two things that are computed in two completely different ways, and then you have miraculously the postulated equality that pops up as a result, as well as highly non-trivial predictions, which we are able to prove systematically. And once again, in the example of P2 with a line and a conic, well, on the log side, I said that this log invariance should be computed from the scattering diagram. They should be computed in terms of the log Gromov Witten theory of the toric model associated to this. And one way of constructing the toric pair for P2 and the line and the conic is you can blow up the intersection points of the line with the conic, well, first once, and then for the strict transform of the line. And then you can contract the -1 curve that you get as a result. And that's the sort of circuits of link construction that I was mentioning before. So that will give you a birational morphism where from F2, the second Hirzebruch surface with a toric boundary, to P2 with a line and the conic. And this morphism is an isomorphism on the divisor. So the resulting scattering diagram is essentially given by the fan of F2 with one focus singularity, which remember the contraction of the line. And the computation of 2D choose D, the numbers that are shown on the table for log Gromov Witten invariance for P2 and the line of the conic is given by considering the transport against the wall generated by this focus singularity of the asymptotic monomial corresponding to the conic. And that's by theorem of Mandel. That's what Michel was mentioning in the chat, or probably no, he was mentioning. He was just saying it. This binomial coefficient gives you the log Gromov Witten invariance, and the Q deformation is given by promoting everything to their Q analogs. Now, if you try and do the same thing from the open side, you just rewind back to the cartoon that I presented of P2 with a line and a conic. And what it said is that the local invariance of P2 of O-2 plus O-2, sorry, O-1 plus O-2 on P2 are given by the open Gromov Witten invariance of one toric brane on the framed vertex at framing 1. And we can compute these. So we just have one connecting component of the boundary winding around d times around the S1 in this toric Lagrangian. And so the topological vertex calculation is standard. You have a short function contribution of the shift by framing. So if you want to convert to winding numbers to the winding number representation, you have a factor, well, a representation theory factor given by the character of the symmetric group for the length d. So the full conjugation of length d in the representation R, and this localizes on Hooke-Young tableaus. And so you just have the sum over hooks. And the expression for the short function in that case is known due to Stanley. And it's some Q binomial expression. And the use of the Q binomial theorem gives you, again, the Q2D choose the Q binomial up to some factor. And this factor is exactly the log local open, well, the log open higher genus version of the log local correspondence.
So you have one toric brane in C3.
Correct.
And what's the other thing?
Well, the other thing,
the other component of the divisor gives you what?
Oh, that's what you use to construct the Calabi Yau threefold. You take O minus 2 on the complement of, so you take O minus the conic on the complement of the line inside P2. So you have O minus 2 on C2, which is just O on C2. So it's just C3. Okay. Oh, that's 2 hours already, is it? Yeah. Yeah, let me just mention 3 quick applications. So there are some implications for some open problems in both for the local and the log theory. One application in particular is that there are various ways of trying to define Gopa-Kumar Vafa invariants of higher dimensional Calabi Yau manifolds, depending on who you are. And the crudest one of which is through a multi-covering formula in terms of the genus 0 local invariants. So for L equals 1, this is just the multi-covering formula for the genus 0 Gopa-Kumar Vafa invariants in terms of the genus 0 Gromov Witten ones. So mu here is the Möbius function. And by the genus 0 log local principle, this takes this form in terms of the log invariants. And conjecturally, so it was conjectured by Klemm Pandharipande in 2007 that these invariants should be integers. And so a proof of this was obtained in the case of compact Calabi Yau n-folds using symplectic methods by Ionel Parker. Our cases are non-compact, probably their proof adapts to those as well. And the first application I want to mention is indeed there's an fully algebraic geometric proof that applies to the case of local surfaces, that this higher dimensional Calabi Yau targets that we're looking at. And the reason for that is that the statement of the log local open correspondence in genus 0 is that these open invariants given by counts of disks or annuli, so in general you have L-1 components. You can define in terms of this some open Gopa-Kumar Vafa invariants. This the content of the later sections of Ooguri Vafa, and later explored by Labastida Marino Vafa. So these go under the name of Labastida Marino Ooguri Vafa invariants. Now, we know that the genus 0 open Gromov Witten invariants coincide with the local invariants with proportionality factor equal to 1, and they have the same proportionality factor relating to the log invariants, and the associated BPS invariants are computed by exactly the same formula. So one consequence of the local open correspondence is that this Klemm Pandharipande invariants of or Ionel Parker invariants for higher dimensional Calabi Yau manifolds coincide with the open with LMOV invariants of toric branes in the toric Calabi Yau threefold. And there's been a lot of attention in the last few years in the correspondence relating Donaldson Thomas invariants of symmetric quivers to the LMOV invariants for not conormals in the conifold, which was generalized to the case of toric branes on toric Calabi Yau threefolds with trivial fourth homology, which is always the case in our setting. So without doing anything, one consequence of the log local open correspondence is that this Klemm Pandharipande invariants of surfaces, of local surfaces, are DT invariants of quivers. And in particular, their conjectural integrality follows for free from the fact that these DT invariants, I'm being slightly cavalier here about the sign, but that doesn't change the content of this corollary. the integrality or non-negative, well, the fact that they're natural numbers after the theorem of Efimov entails that the integrality of the KP or Ionel Parker invariants for these non-compact Calabi Yaus, entirely in terms of algebraic geometric methods. For example, the case of, again, run an example of P2 with line and conic. The dual open geometry is the frame vertex with one brane at framing 1. And you can read off the adjacency matrix of the quiver in the knots quiver's correspondence from essentially the fan of the toric variety, or the intersection matrix of divisors in P2 with line and conic. And in this case, you just get a 2-loop quiver, just essentially the second simplest quiver you can write down. A second application is towards there's been some effort in trying to define Donaldson Thomas invariants for higher dimensional Calabi Yau varieties using moduli spaces of one-dimensional Gieseker stable sheaves. And so first in some examples by Cow and Jung, then in greater generality by Boris of Joyce, and lastly there was an algebra geometric construction by Owen Thomas last September. And it was conjectured by Cow, Malik, and Toda that this DT invariance of fourfolds should coincide with the Klemm Pandharipande invariance of the previous slide, defined through the multi-covering formula. And for local surfaces, this was checked initially by Cow, Malik, and Toda, and then it was checked extensively in greater generality and for higher degrees by Cow, Kuhl, and Monavari. And their comparison using stable pairs hinges in the calculation of the right-hand side on the calculation of this omega d's starting from, again, the log local open calculation in the previous slide. And finally, this was all about genus 0, but one could try and compute, one can try and ask themselves, what is is there similar refined integrality statement that we can make for the full higher genus theory? And so you can define higher genus BPS partition functions, which are obtained, again, the form of the higher genus log local, log open prefactor is given by promoting all that is in this expression to their Q analogs, starting from the Q to 1 limit. And a priori, these have no reasons at all to be integral Laurent polynomial, which would be the expectation, but that's actually true. And that follows from a direct arithmetic proof starting from the log open calculation. And it's already late. So final thing I want to say, everything I said about varieties holds true by replacing variety with the Lee-Mumford stack. So we only had 19, well, we had a classification of 19 cases of Neff-Looijenga pairs, 16 of which are tame, but we can get an infinite list just by playing with singularities. And one example is, well, you can take the weighted projective plane with weights 1, 1, and n. You can take D1 to be the toric divisor that connects one smooth torus fixed points with the torus fixed point with stackiness mu n. You take D2 to be a smooth member of the linear system generated by the other toric divisors. And you can run the correspondence through this example as well. There's an open geometry, which is just the vertex with framing n in this case. And the corresponding quiver is the n+1 loop quiver. So conclusion, for an F-tame or tame Looijenga pair, the log Gromov Witten invariants coincide with the local Gromov Witten invariants up to some universal factor. And in genus 0, they are the same as the open Gromov Witten invariants of an associated toric Calabi Yau 3 with some brane setup. And in particular, the higher genus log invariants with insertion of lambda classes coincide with the higher genus open invariants through a natural refinement of the prefactor relating the log and the local ones. And moreover, the BPS invariants that you can extract from these generating functions are generating functions of DT invariants of a symmetric quiver and of a Klemm Pandharipande, Ionel Parker, Labastida Marino Ooguri Vafa invariant in the relevant context. And moreover, all these invariants are closed form computable, and actually they are closed form computed. There's some master formula that encompasses them all for the case of the Neff pairs and the local invariants, and for the tame invariants in all the other contexts, including higher genus. And that's all I wanted to say. And I have a bunch of questions. The first one was already asked by Mina. So what happens when you don't stick to the case of a surface? I don't have an answer for this first one. I'm starting to have some preliminary answers about the second one, which is how about giving up this Neffness condition and possibly the tameness? And we're gathering some very convincing evidence that there can actually be a broader list of cases where the set of correspondences will hold. And one somewhat unsatisfactory point in all this discussion has been that everything can be computed with a lot of muscle. And it's beautiful to have closed form solutions for everything, but one would like to understand this sort of principle geometrically, or in terms of some algebraic structure underlying both, say, the log and the open theory. And the appearance of the quiver is completely mysterious from the vantage point of the theory of the surface, and it would be nice to elucidate that as well. Okay, that's it. Thank you very much.
Questions?
Yep. So I wasn't keeping track of the chat, so maybe I just have a look.
So one question I have is this discussion about, I'm just curious, you mentioned briefly that you thought maybe okay, so I'm supposed to think of these log invariants as a rigorous way to define open Gromov Witten invariants. And you mentioned that at least because of this tangency condition, it's easier to define them ad infinity in the Coulomb branch. But is there any prospect for using this to define open Gromov Witten invariants in the interior of the Coulomb branch?
So if I understand your question, one could try and ask, for example, so when you say in the interior of the Coulomb branch, so thinking geometrically, instead of sitting in the deep interior of the Kähler cone of my variety, I can try and see what happens when I approach some singular phase. And is that what you have in mind?
It wouldn't even have to be a completely singular phase, right? Just the well, okay. Yeah, just anywhere, like there are walls.
Yeah. So one question is what is so this, all these equalities are some sort of perturbative equality taking place at some point around large volume limit.
But if the log invariants are really more in the open Gromov Witten picture, then there doesn't seem to be any reason why those should care about being at infinity in the Coulomb branch.
Yeah, so I'm just trying to think of an example because so I had the C3 in mind. So if one took, for example, the case of the blow up at one point of the plane, in that case, you
can just do local P1 with the brain in the middle.
Yeah, that's what I was doing. So the dual open geometry would be the result conifold. So the question is, if I consider the limit in which I shrink the Kähler parameter to 0, so look at a singular conifold, and I look at the discount for the toric Lagrangian in that limit,
You don't have to make it singular. Why do you make it singular?
Sorry, I
Right,
thought
yeah,
that.
I'm just asking about any chamber besides the chamber at infinity.
Yeah, but result conifold has, okay, the result conifold is has two chambers, but they're just flops of each other, which are isomorphic, which give you the same variety.
Yeah, so I'm just,
um,
I mean, like, for example, for the manifolds studied by Klemm et al., that this is definitely not the case. There are all sorts of interesting chambers.
no, but I think because everything is toric, it doesn't really make a difference. You can have multiple. So if you can have multiple chambers, but no, sorry, but what I'm saying is not correct. So I'm just trying to come up with an example where I have a secondary fan with two smooth cones corresponding to two non-isomorphic large volume points. Is there an example for toric Calabi Yau threefolds off the top of your head? So what is the manifold of Klemm et al. That you have in mind?
I mean, physically, I'm just saying the you can think of geometrically engineering the Minahan-Nemeshansky theories or their 5-dimensional variants. So those certainly have all sorts of interesting BPS spectra and wall crossing phenomena.
Yeah, I'm not sure I can say anything sensible about what happens to the log theory in that setting.
So I don't know if this answers the question, but if you think about having an SYZ base, and if you think about the scattering diagram being the SYZ base, then you can make sense of like having disks that end in or on some chambers of the interior, which and the counts of those disks would be different. But then when you get to infinity, that count will go like through some wall crossing and eventually stabilize.
Right.
And maybe, yeah.
Yeah, that's exactly what I'm asking about, is if the log theory can be generalized to study counts in the interior.
So you can do this in the sense if you define your counts in the interior as being counts of tropical disks inside the scattering diagram, then yes, you can, but I'm not exactly sure in what generality. Certainly it hasn't been done in full generality. But then here we're again using some sort of substitute count where we are now counting tropical disks. And maybe in the examples that we saw today, it didn't really make a difference because you don't have that much scattering. But if you had a lot more focus singularities, then you would start seeing a difference. Maybe the log invariants are the ones where you're just like so close to the boundary and you exactly know what is missing, because all you have to do, you have to like add like a little disk in the normal bundle of the divisor to like close it up, something like this. But anyways, to answer your question, if I understand it, you have a scattering diagram. It's the base of your SYZ vibration. You can define disks that end anywhere. You can count them, tropical disks, and then you can declare this to be your count open Gromov Witten invariant if you desire. So I don't know if that's helpful.
Yeah, but that's not making use of this log definition, right? That's using this tropical geometry picture.
That's correct. And then when the thing is, then when you go to infinity, these tropical disks turn into tropical curves. However, I guess what I want to say is that the correspondence between a tropical curve and log Gromov Witten invariant is not like established in all cases. So in summary, whenever you have a correspondence between log Gromov Witten invariance and counts of tropical curves, then you can cut off your tropical curves before they reach infinity and declare this your count of open disks, tropical disks. But that correspondence is, I think, is maybe you have it for like P2 relative to a smooth elliptic curve, but not in general. As of yet, but maybe eventually it will. So you may have, I don't know, maybe you mentioned you sat in some talks of Bousseau, and there is some story like this in some of his work.
Yeah.
So yeah.
Yeah, I was just curious if this log, the generality that this log technology could be generalized to.
It's next to question. I mean, there's the potential is unlimited. Let's say, yeah.
Okay, any more questions? Okay, if not, let's thank Andrea again. This is thanks for sharing us the story. I look forward to hearing more.
Thank you.
Okay. Thanks, Michelle, also as well. Okay.
Thank you.
Bye-bye. Bye, everyone.
Bye. Bye-bye.